Today we're going to be talking about how to sketch a quadric surface and its traces and how to describe the figure. And in this particular video, we're going to be sketching 3 different quadric surfaces. The first one we're going to tackle here is x squared plus z squared is equal to 1. I have a chart that'll help us sketch some of these surfaces, so let's take a look at it. Keep in mind that our formula here is x squared plus z squared is equal to 1. If I look at this chart here, it describes some quadric surfaces. So for example, the ellipsoid, cone, cylinder, elliptic, paraboloid. There's some others down here near the bottom as well that are off the screen. But it gives me the standard form of the quadric surface and the shifted form and some information that I can use about the traces, how to determine the axis of the quadric surface, and just some additional tips or notes about the quadric surface. So what I notice here is if I look at the standard form column in my chart, I notice that all of these standard forms have 3 variables involved. They all have x, y, and z. However, when I get to cylinder here, I notice I only have x squared and y squared. A and b here are constants. Remember that our equation was x squared plus z squared equals 1. That looks awfully similar to the standard form of this cylindrical quadric surface. What this tells us over here, if we go to the axis set by column, it tells us that the variable that does not appear in the equation is the coordinate axis around which this cylinder is centered. So notice here I have this vertical cylinder that's centered around the z-axis and the cylinder never touches the z-axis. That corresponds to my standard form equation here where I have x squared and y squared but no z variable. So for our equation, when we have x squared plus z squared, we're going to have this same cylinder except that it's going to be tilted to be centered around the y-axis instead of the one we've got pictured here, which is centered around the z-axis. So let's go back and take a look at our equation here. We want a cylinder that's centered around the y-axis like this, so we can go ahead and draw a picture of this cylinder centered around the y-axis. And if we make it 3-dimensional here like this, we can start to get a good picture of what our cylinder might look like here. I'll make it transparent so we can see sort of the back of it. So what this tells us is that because y is excluded from this equation, our cylinder is around the y-axis and it'll never intersect the y-axis. So since y is missing from the equation, the graph never intersects the y-axis. The other thing I know then is that my rulings are going to be parallel to the y-axis. So since my graph never intersects the y-axis, I know my rulings are parallel to the y-axis and I can draw the rulings on my cylinder like this. Now let's take a look at our other 2 equations here. We'll start with z is equal to 1 minus y squared. It doesn't fit our chart of quadric surfaces as easily, so we'll have to do a little bit more work with the equation itself. But what this equation tells us is first, there's no x variable involved in the equation. X is missing. And that tells us that our graph is never going to intersect the x-axis. Because our graph never intersects the x-axis, we know that our rulings are going to be parallel to the x-axis. What else do we know? We know that no matter what value we plug in for y, we're going to get 1 minus some positive value because we're going to square that value. So that means no matter what y value we plug in, z is always going to be less than or equal to 1. So z equals 1 is the highest value that our graph is ever going to attain. So let's say that this is z equals 1 right here. This is the highest value, which means the graph is only going to fall from here. We know that the rulings are going to be parallel to the x-axis and that the graph won't intersect the x-axis. And we also know that no matter what value we pick for y, for example, if we pick 1 for y, we're going to get 1 squared is 1, 1 minus 1 is 0. If we pick negative 1 for y, we're going to get negative 1 squared, which is 1, 1 minus 1 is 0. So for both positive and negative 1, z is going to be equal to 0. And that's true for every positive negative pair that we pick for y. So y equals 2 and negative 2 are going to give us the same z values. Y equals 3 and negative 3 are going to give us the same z values. So there's a pair of y values that'll produce the same z value for us every time. And if we think about what that's going to look like, it's just this graph here where we have a downward facing parabola like this. It's going to run through this point that we indicated here, the highest point where z was equal to 1, and come down like this, and it'll continue on for more and more negative values of z. But if we make this transparent, this is going to look like this. And now if we draw our rulings, they're going to be again parallel to the x-axis because x is missing from our equation. And so we have our rulings like this. Now let's take a look at our third equation here. We have x times y is equal to 1. Immediately we see that z is missing from the equation. That tells us that our graph is never going to intersect the z-axis, and therefore that our rulings are going to be parallel to the z-axis. The other thing we know is that in order to get a positive 1 over here on the right-hand side, x and y have to both be positive or both be negative. So if we go ahead and draw the negative directions of the x and y axis, so if we go like this and draw these negative directions, this is still the y-axis and the x-axis here, but this is x in the positive direction, x in the negative direction, y in the positive direction, y in the negative direction, so we can put positive signs here. Since x and y both have to be positive or both have to be negative, that tells us that our graph is going to occur entirely in the first and third quadrants of our xy coordinate plane. We also know that in order to equal 1, x has to be large when y is small, or y has to be large when x is small. So as an example, if we take x equal to 10, then y has to be equal to 1/10. There, x is large and y is small. If we take x equal to 100, then y has to be equal to 1 over 100. So as x gets larger and larger, y gets smaller and smaller, and vice versa. If y is equal to 100, then x has to be equal to 1 over 100. So as y gets very large, x gets very small. So here's what that ends up looking like. We can go ahead and draw a picture. In the first quadrant here, it's going to look something like this, because remember, as x gets very large, as x goes out this way in the positive direction and gets very large, y is very small, so y is going to be close to 0 here. And then the opposite is true. As y comes out in the positive direction this way and gets very large, x has to be very small. So we have this trace of it here, but now we just need to make it three-dimensional and bring it up here parallel to the z-axis. Remember, our graph will never intersect the z-axis, but it's going to look something like this. And my rulings here are going to be parallel to the z-axis. I also want to go ahead and draw a picture of what the graph will look like in the third quadrant of the xy coordinate plane. If I draw it slightly larger than I did this one, and we'll do this dash so that it looks like it's behind it here, we'll draw this three-dimensionally like this. So that's in the third quadrant, and then my rulings are like this, again, parallel to the z-axis. So again, that's just a couple examples about how to describe the figure and sketch the surface and its rulings.